Albert Einstein's view, often referred to as local realism, emphasized the existence of an objective reality and the notion that particles have inherent properties independent of measurement. According to Einstein, particles possess definite properties such as position, momentum, and spin, regardless of whether they are being observed or measured. He believed that there should be a complete and deterministic description of physical systems and that hidden variables might explain the seemingly probabilistic behavior observed in quantum mechanics. The view of Einstein and many others was the universe is real, the particles, electrons, and protons have definite properties that are inherent to them, regardless of if they are being measured. Essentially, that if a tree falls in the forest and no one is around to hear it, does in fact make a noise. In contrast, Niels Bohr, a prominent physicist and one of the founders of quantum mechanics, held an instrumentalist or anti-realist position. Bohr argued that the properties of particles such as position and momentum are only meaningful in the context or observation. According to him, quantum mechanics provide a probabilistic framework that describes the statistical outcomes of measurements, rather than revealing the true nature of particles themselves. Bohr emphasized the importance of complementary, which suggests that different experimental setups reveal different aspects of a particle's behavior, and that these aspects may seem contradictory when viewed individually. For examples, a Schrödinger's cat. Imagine a box containing a cat, a vial of poison, and a radioactive substance that has a 50% chance of decaying within a specific time frame. According to quantum mechanics, until the box is opened and the cat is observed, the system is described as a superposition, where the cat is both alive and dead simultaneously. From Einstein's perspective, this situation is absurd. He believed that the cat must be either alive or dead, regardless of whether someone observes it. Einstein argued that there should be hidden variables determining the state of the cat, even if they are not directly observable. Einstein believed in an underlying reality with definite properties, while Bohr emphasized the role of observation and measurement in defining the properties of particles. Einstein's argument against certain aspects of quantum mechanics, as presented in the EPR paper published in 1935, focused on what is commonly referred to as entanglement. The EPR paper presented a thought experiment involving two entangled particles. According to quantum mechanics, two particles can become entangled, meaning their quantum states become correlated. This entanglement implies that measuring one particle instantaneously affects the state of the other, even if they are physically separated by a large distance. Einstein and his colleagues Boris and Nathan Rosen argued that this behavior violated the principles of locality. Locality in this context refers to the idea that physical effects should only propagate at speed equal to or less than the speed of light. In other words, no information or influence should be able to travel faster than light. Einstein's argument relied on the notion of hidden variables, which he believed should exist and determine the properties of particles even if unobserved. He proposed that there must be hidden variables governing the behavior of entangled particles, and that the seemingly instantaneous correlation between their measurements was an indication of an incomplete description of quantum mechanics. In the EPR paper, Einstein's Boris and Rosen described a hypothetical experiment to demonstrate their argument. They suggested measuring one observable of one particle and claimed that through knowledge of this measurement one could predict with certainty the value of a corresponding observable of the other particle, even if separated by a large distance. They concluded that this implied the existence of elements of reality that were not accounted for in quantum mechanics. Later in 1964, physicist John Bell developed a theorem known as Bell's theorem, which provided a way to test the predictions of quantum mechanics against Einstein's proposed hidden variables. Subsequent experiments such as Bell tests have shown that the predictions of quantum mechanics hold, indicating that local hidden variables theories are incompatible with the observed behavior of entangled particles. This has led to the acceptance of quantum entanglement and the rejection of local realism as described by Einstein's views. The CHSH experiment, named after the initials of its author, John Clauser, Michael Horn, Abner Shimoni, and Richard Hall, is a variation of the Bell test experiment. It was designed to test the predictions of quantum mechanics against the concept of local realism. The experiment involves measuring correlations between two entangled particles, typically referred to as particle A and particle B. The goal is to determine if the observed correlation between the measurements of the particle can be explained by local hidden variables or if they require no local effects. In the experiment, two observers, Alice and Bob, each have a measurement apparatus that can measure a specific property of their respective particles, such as spin. They are free to choose the orientation of their measurement devices independently. The CHSH inequality, which stands for Clauser, Horn, Shimoni, and Holt inequality, is a mathematical expression derived from local realism assumptions. If the measurement obey the predictions of local realism, the CHSH inequality should hold. However, if the measure violates the CHSH inequality, it indicates that local realism is not compatible with the observed correlations supporting the predictions of quantum mechanics. The CHSH inequality is expressed as where S is the correlation value calculated from the measured outcomes of the particles. If the measured correlation value exceeds 2, it suggests a violation of local realism. Experimental tests of the CHSH inequality have been conducted and the results consistently demonstrate violations of the inequality, indicating that the observed correlations between entangled particles cannot be explained by local hidden variables alone. These violations support the predictions of quantum mechanics, which allow for non-local correlations between entangled particles. According to the theories and experimental tests, including the CHSH experiment, it is concluded that local realism, which assumes the existence of hidden variables and the restriction of information propagation to speeds slower than or equal to the speed of light, is incompatible with the observed behavior of entangled particles. This implies that faster than light communication is not possible within the framework of quantum mechanics.